will complete the heat transfer part with the thermodynamics part, heat and thermodynamics part, with the discussion about the heat engines and Carnot cycle, and later the reverse heat engines and refrigeration cycle in particular. And with this, we will complete heat and thermodynamics. The next thing will be heat transfer, which will be about conduction and radiation. So let's continue ahead from the discussion last time. So we had seen the two types of cyclic processes, the heat engine type of cyclic process and the reverse heat engine type of cyclic process. And further, we had defined the parameter of efficiency of a heat engine. So we will take it forward from that point onwards today. So let's continue. So cyclic processes, we had seen PV cycles, which are clockwise, which are heat engine cycles, where Q net or W net during the cycle is a positive quantity. And then, of course, we had seen cyclic processes where the PV cycle was anti-clockwise, or the PV closed loop was anti-clockwise. So these are refrigeration cycles. Where Q net is equal to W net is a negative quantity. Okay. Now further up, we had seen about heat engines. A heat engine is a device that converts heat energy into mechanical work by continuously running a cyclic process, which is having net work done by the gas positive. So the cyclic process runs between a heat source and a heat sink, where the heat absorbed from the heat source during one cycle is Q1, whereas the heat dissipated into the heat sink per cycle is Q2. So the net heat exchange during the cycle becomes Q1 minus Q2. Okay, and since Q1 is greater than Q2, it is a positive quantity, whereas the work done per cyclic loop is equal to W. So we have W is equal to Q1 minus Q2. That is the first important aspect of a heat engine cyclic process. And secondly, we define the efficiency of the heat engine as the ratio of work done by the cycle, the net work done, per unit heat supplied from the heat source. So therefore, it also becomes 1 minus Q2 by Q1. So we can define the efficiency in terms of W and Q1, or we can define the efficiency in terms of Q2 and Q1. Both these formulae are equally valid, and they're one and the same thing. Okay. So today we'll start with some applications of this particular concept here. I'm just sending you the notes of the last lecture also. I'll send it to you in the group. I'll just send it in a few minutes. Okay, so let's look at an example situation of this. So suppose we have a very simple PV cycle. And when I say very simple, I mean it is literally a rectangular loop. So we have a PV cycle which is in the shape of a rectangular loop with the progression of the cycle going in the clockwise direction, as you can see. So given that this pressure is P naught, volume V naught, and in comparison, this pressure is, let us say, 4 P naught, or let's say 3 P naught. Okay, whereas this volume here is 4 V naught. Okay, so an ideal monoatomic gas, okay, undergoes the cyclic process ABCDA. Okay, so calculate the efficiency of the cycle. So actually, we will first calculate Q net for the cycle and Q1 and Q2. So Q1 is the amount of heat absorbed by the gas in the cycle, whereas Q2 is the amount of heat dissipated by the gas, or by that you can say lost by the gas in the cycle. So just note down the question and try to figure out how we will calculate these things, and finally we'll calculate the efficiency. Okay, so we'll discuss this in a moment. Just try to figure out what all formula etc. we'll use over here. Okay, so let's understand here. So we will require the PV diagram in detail to understand everything. So copying it down here. So now we need to understand that in which part of the process heat exchange is positive, that is heat is supplied to the gas, and which part of the process heat exchange is negative. So heat is withdrawn from the gas. So we can see that AB, it is a isoporic heating. Okay. Temperature at B will be greater than temperature at A. Okay. So QAB is positive and equal to NCV delta T. Okay. So now we can also see that if temperature at A is equal to T naught, then temperature at B is equal to PB upon PA times temperature at A. Okay. Because temperature is directly proportional to, so during this process AB, temperature is directly proportional to pressure. So that is how we understand this. Okay. So that means temperature at B will become 3 P naught because the pressure is becoming triple. Okay. So this quantity will be equal to N into CV, which is 3 by 2 R into 3 T naught minus T naught. That will become 3 times NR T naught over. Okay. This is QAB. So we can also represent it like this, that heat is coming into the gas during the process AB. Similarly, we'll see during the process BC also some amount of heat is coming into the gas. Okay. Because next thing we'll see is that BC is which type of process now? BC is an isobaric expansion. Okay. So it is also a process where temperature is increasing. So QBC will also be positive, just like QAB was positive. Okay. So during BC, what is happening? That temperature is proportional to volume. So that means temperature at C will be the ratio of these volumes times temperature at B. So temperature at C will become 4 into 3, 12 T naught. So the temperature at A was T naught. Then we are learning that the temperature at B is becoming 3 T naught, and the temperature at C is becoming 12 T naught. So from that we can see that QBC is N CP delta T. So monoatomic gas, so N into 5 by 2 R into 12 T naught minus 3 T naught. So N into 5 by 2 R into 9 T naught, or 45 by 2 NR T naught, or 45 by 2 P naught V naught. Okay. So that is our QBC. And as I told you, it's a positive quantity. Now, like I've done the calculations for these two, now I want you to show that in the other two processes, heat is coming out. Q will be negative. Okay. And I want you to calculate how much these are. Okay. QCD and QDA, they will both be negative. Okay. And once we find out how much these are, then we can see that, okay, the Q1 for the entire process will be QAB plus QBC, whereas Q2, the heat dissipated into the heat sink, will be magnitude of QCD plus magnitude of QTA. So just note down up to here and do the calculation for QCD and QDA, please yourself, and tell me how much it is. Yeah, anybody got the answer for these two? Now at the point D, you can see the temperature will again become equal to how much? So you can see for C to D, temperature is proportional to pressure. So temperature at D upon temperature at C should be pressure at D upon pressure at C. So temperature at D will become, pressure is coming down to 1/3. Okay, so the temperature will be 40 now. Okay. So this temperature TD will be equal to 40 not over here. So this will become, so that is my QCD. Likewise, I would like you to calculate yourself the value of QDA, how much that will be. Because with that, we can complete the problem now. Okay, very good, Kunj. Just check your answer for CD once more, please. DA is correct. Okay. Okay, so DA is, it is an isobaric compression. Okay. The point D had pressure P naught, volume 4 V naught, and temperature 4 T naught. The point A had P naught, V naught, T naught. Okay. So above you can see that. So this is the state change. Okay. So QDA will be NCP delta T. So N into 5 by 2 R into T naught minus 4 T naught. So that is minus 15 by 2 NR T naught. Okay. So QDA is equal to minus 15 by 2 NR T naught or minus 15 by 2 P naught V naught, however we write it. Okay. So this is this quantity. So now we can understand that for the cycle ABCDA, Q net is equal to W net is the sum of these three, okay, these four rather. So okay, so it is 3 plus 22.5 minus 12 minus 7.5 P naught V naught. Okay. So it is okay, so it's positive as expected. So that's the first thing. Then Q1 is, so that is equal to whereas Q2, the heat dissipated is equal to magnitude of CD plus DA. So that will be and from that we have you already know is 6 P naught V naught. So efficiency is W by Q1 or this, whatever way we write it. So it is 6 upon 25.5, or you can say efficiency percentage is nearly 24%. So I'm just minimizing this a little bit, just go through this carefully. Make sure the calculation of each of the terms is clear. and also the method. Okay, so these type of questions are quite important. We will discuss a few more of these, and through this discussion, we will also once again look at the applications of various different formulae. Like in this question, we are seeing the formula for isobaric and isochoric processes in detail. Okay. All right, let's look at another example. So now this time given to us a PV graph. With a situation like this, the second process is curved like this. Such that finally the third process is a straight line process like this. So BC is a process where pressure is inversely proportional to root V. Okay. BC is a polytropic process with pressure inversely proportional to root V. Okay. So a monoatomic gas undergoes the cycle KVCA, where the pressure at B is 2 times the pressure at A, and the volume at C is 4 times the volume at A. So if temperature at the point A is equal to 100 Kelvin, find temperature at B and temperature at C. And second, find the efficiency of the heat engine. So again, this is a good question to understand and apply all the concepts, including the concepts of polytropic processes, which we've been discussing in the last couple of lectures, including previous lecture. We've done a couple of questions based on this. So please learn to apply those things over here. And finally, also calculate the efficiency of the heat engine, which is something that we are learning today. Okay. So just give this question a try, people. I'll put up the answers in a few minutes. So make sure you try out the question till then. Okay, very good. Kunj, you have got the answer. Okay. So let's understand. So the temperature at A is equal to 100 Kelvin. Now we can see that this information given. Now because AB is isochoric, so pressure is proportional to temperature. So PA by PB should be equal to TA by TB. So from this we will get that temperature at B is 200 Kelvin. Okay, so now we know that the temperature at B is 200 Kelvin. Okay. Now we'll come to the process AC. So P is inversely proportional to root V, means pressure at B divided by pressure at C should be equal to square root of volume at C divided by volume at B. Okay. So now we can see that the pressure at C is equal to the pressure at A, because this is a horizontal straight line. Okay. So if you connect that here, we'll see that root of VC by VB is equal to PB by PC, which is actually PB by PA, okay, which is actually 2. That means VC should be equal to 4 times VB. Okay, or that's the same thing as 4 times VA. This is already given to us, okay, so that's fine. Okay. Now we can see that PB VB upon TB is equal to PC VC upon TC. So from that we'll understand that the temperature will become 2 times the temperature at B. So temperature at C will become 400 Kelvin. So we got this fact now, that the temperature at C is 400 Kelvin. Okay. Okay, now once you have understood this, now let's come to the efficiency part. So for the efficiency, we need to calculate W by Q1 or 1 minus Q2 by Q1. So how do we do that? So we can first of all understand that W is very easy to calculate. Okay. From the above graph, you can understand this will be 0. This will be NR delta T upon 1 minus half. Okay, because PC is a polytropic process. PV to the power alpha is constant, where alpha is equal to half. So work done during the BC is NR delta T upon 1 minus alpha. That formula, okay. So that will actually be NR delta T upon 1 minus half, or that is 2 times NR delta T. So that is 2 times NR Tc minus Tb, like this. Okay, so we'll come back to this. Okay, whereas work done in the process Ca will be NCP delta, will be P delta V, because it is a isobaric process. Ca is isobaric. Okay, so Q is NCP delta T and W is P delta V. Like this. Or that is the same thing as NR delta T. So now let's put together this information. So W for the cycle is going to become NR upon 1 minus half, that we have, into Tc minus Tb plus NR into Ta minus Tc. This one, this is this one. So 2 times NR. Now, if you remember, the temperatures are 400 and 200. And here the temperatures are 100, 400. Okay. Temperatures at ABC, you can see, are 100, 200, and 400. So 400 minus 300. So you can write the work done like this also. Or we can write the work done as P naught V naught, because pressure at A, suppose it was P naught, volume at A was V naught, temperature at A was 100. So TAVA is NRTA. So from that we can see that 100 times NR is equal to P naught V naught. We can write it this way also. Okay. Now similarly, I want you to calculate Q1, because we'll calculate the efficiency by this formula, W by Q1. So once again, the tricky thing is, for Q1, you have to understand which part of the process heat is supplied to the gas and which part of the process heat is withdrawn from the gas. Okay. So for that, we have enough information about the individual processes A, B, B, C, and CA. So you should be able to visualize or calculate it from that. So just try it out. Okay, so let's once again understand here that during the process AB, you can see isochoric heating. So heat will be coming into the gas, heat will be positive. During the process BC also, you can see temperature is increasing and C is positive. For the process BC, the molar specific heat capacity is CV plus R upon 1 minus alpha. So it is 3 by 2 R plus R upon 1 minus half. So it is 3 by 2 plus 2. It is 7 by 2 R. So it is that type of process where C is positive and delta T is positive. So Q is positive for the process BC. So QBC is positive, so heat is coming in. Whereas during this part, heat is going out. QCA will be negative, but these two will be positive. So from this, we can understand that for this particular process, Q1 will be QAB plus QBC because QAB is positive, QBC is positive, but QCA is negative. So these two will come part of this. Okay? So QAB will be NCB delta T, QBC will be NC delta T. That is N3 by 2R into this temperature difference, and this will be N7 by 2R into this temperature difference. So we just understood that BC is a process where PV to the power half is constant. So C is equal to CV plus R upon 1 minus alpha. So from that we are getting it as 7 by 2R. That's how we are getting this. Okay. So now let's just substitute the quantity. So 3 by 2 NR into this temperature difference is 200 minus 100, and 7 by 2 NR into this temperature difference is 400 minus 200. So this will become 3 by 2 of 100, so that's 150, plus this is 200 into 7 by 2, so that's 700. So 850 NR, that is Q1, whereas W was 100 NR. So we can see now the efficiency two by 17, or if you convert that to a percentage, you can see that it will be nearly 11.76%. That is the efficiency. So very good, Kunj, your answers were correct. Okay, people. So hope this question is clear. Now let's move on to a specific type of heat engine called the Carnot engine or the Carnot cycle. I'm sure you have heard about this in chemistry also. So this is a very specific type of a heat engine wherein the cyclic process consists of two isothermal processes and two adiabatic processes. So the particular PV cycle in concern, it consists of, say, an isothermal process which is like this. So E to B is an isothermal expansion, okay, at temperature T1, let's say. Then B to C is a adiabatic compression. And then again we have an isothermal process, but this time, sorry, adiabatic expansion, not B2C. You can see the volume is increasing, so it's again an expansion. And then of course the next process is a compression, which is, let's say, like this. So C to D is an isothermal, but this time the volume is decreasing, so compression at temperature T2. So this one is having a temperature T2. And finally, this process here is again an adiabatic process. Okay. So typically it will look more like this, let's say. So D2A is again an adiabatic process, but this time it's an adiabatic compression. So it's a heat engine cycle consisting of two isotherms and two adiabats. Okay. So what is happening is that the process within the engine of the heat source supplying the heat source operates at uniform temperature T1. So Q1 amount of heat is supplied to the cycle through an isothermal process. Okay. So that is the amount of heat coming into the system, Q1 over here. Whereas Q2 amount of heat is dissipated into the heat sink. Now the heat sink is also operating at a constant temperature T2. So this Q2 amount of heat is going in here. Okay. Whereas, okay, so you can see that QBC is 0 and QDA is 0 because these are adiabatic processes. Okay. So Q1 is equal to QAB and Q2 is magnitude of QBC. Sorry, QCD. Okay. And the efficiency is 1 minus Q2 by Q1. Now this efficiency here actually becomes 1 minus T2 by T1. So this particular formula is for a Carnot cycle. Now we will look at the proof of this formula also, but first note this down. It's quite easy to prove this, that 1 minus Q2 by Q1 will be the same thing as 1 minus T2 by T1. Okay, so let's look at the proof of this formula. So in this, we understand that Q1 is equal to QAB. So that is nRT1 natural log of VB by VA, right? You can see that in the above process. If you just compare these two, and Q2 is magnitude of QCD. So that is nRT2 ln of VD by VC. This whole thing is mod. Okay. Now, when we calculate this thing, one thing which is important is that if we take log of the ratio of two things, this is a negative quantity if A is less than B. So therefore, the mod of ln A by B becomes minus of ln A by B, which becomes ln B by A. So just as an example, natural log of 3 by 5 is a negative quantity, okay, because 3 is less than 5. So ln 3 is less than ln 5. Okay. So ln 3 by 5 is ln 3 minus ln 5, which will be a negative quantity. So therefore, mod of ln 5, 3 by 5 will become mod of ln 3 minus ln 5, which will become ln 5 minus ln 3, which is ln 5 by 3. Okay. So magnitude of ln 3 by 5, I'm just giving as a numerical example, will be actually ln 5 by 3. Okay. So that's basically this idea here, that this one. Mod of ln A by B, okay, becomes ln B by A, provided A is less than B. Okay. So that is what we'll apply over here now. Okay. So here we'll see that VD is less than VC. Therefore, ln VD by VC is a negative quantity. Therefore, mod of ln VD by VC will become ln VC by VD. This is how we'll substitute. Okay. So this quantity here will become nRT2 mod of ln VD by VC, because obviously T2 is a positive quantity. Absolute temperature cannot be negative. Now next on this, we will apply this concept. So this becomes nRT2 natural log of VC by VD. So that is my Q2. Whereas this one was Q1. And now my efficiency is 1 minus Q2 by Q1. So we'll come to that. So the efficiency is becoming 1 minus T2 by T1, but into this factor, ln VC by VD divided by ln VB by VA. So next what we'll show is that this factor is actually unity. Okay, so this last step you have to understand how this is coming. Because the ratio of these volumes will be same. VC by VD will be the same as VB by VA. So we'll show that next through some equations. So just note down up to here, please. Okay, so next up, let's understand why this step, how it occurs. So now notice that AB and CD, they were isotherms. Okay. So PAVA is equal to PBVB. So that means we can see that VB by VA is equal to PA by PB. Okay. And PCVC is equal to PDVD. So that means VC by VD is equal to PD by PC. That's the second thing. Okay. Now similarly, we can see that BC and DA, they are adiabatic processes. Okay. So PBVB to the power gamma is equal to PCVC to the power gamma. Okay. And PAVA to the power gamma is equal to PDVD to the power gamma. Okay. So if we divide these two equations, we can see here that PB by PA into VB by VA to the power gamma is equal to, on the other side, PC by PD into VC by VD to the power gamma. Okay. So now we incorporate this and this equation here. Okay. So you can see here that PB by PA becomes VA by VB, just the inverse of what we've written here. Okay. And like that for this one also. So this becomes VD by VC. Okay. Which further means that VB by VA to the power gamma minus 1 is equal to VC by VD to the power gamma minus 1, which means that this ratio of volumes is equal to this ratio of volumes. Okay. So this can now further be used to show that ln of VB by VA is the same thing as ln of VC by VD. So therefore my efficiency, which was 1 minus Q2 by Q1, which was 1 minus T2 into ln of VC by VD divided by T1 into ln of VB by VA is nothing but 1 minus T2 by T1. So the efficiency of the Carnot engine should be given by this formula. It is proved in this. Okay, so I'll just take you through this once more. It's a little bit tricky how we manipulate the variables. Okay, so just go through it carefully and make sure you understand all the steps. Okay, so people hope this application is clear. So the only thing you have to be careful about in applications in Carnot engine is when you substitute this formula, efficiency is 1 minus T2 by T1. Please make sure that you are substituting T2 and T1 in kelvins. Okay. Don't make the mistake of substituting in degree C, because you'll get the wrong answer. Okay. So for example, if T1 is given to us as 127 degrees C and T2 is given to us as 27 degrees C. So we should convert this first. That T1 is 400 Kelvin, T2 is 300 Kelvin, and therefore the efficiency is 1 minus, so 1 by 4, okay, or efficiency is 25%. So this is something you have to be very careful about, that make sure you substitute T2 and T1 in the formula only in kelvins and not in degrees C. All right. The next thing is the statement of second law of thermodynamics. For heat engines. Okay. There is a more general statement of second law of thermodynamics, which is in terms of entropy, but that is not in our syllabus. The concept of entropy is not in the physics syllabus. You might have studied in chemistry about entropy. So in physics syllabus, the second law of thermodynamics is defined in terms of heat engines. Okay. The efficiency of a heat engine, of any heat engine, can never be 100%. Okay. It will always be less than 100%. Okay. And part of the statement is another thing. Okay. That if a heat engine operates between a heat source at T1 and heat sink at temperature T2, so obviously T1 is greater than T2, okay, then the maximum possible efficiency is equal to the efficiency of a Carnot engine. Any other type of heat engine that we run will be having an efficiency of less than 100%. I mean, less than Carnot engine. So maximum possible efficiency is when a Carnot cycle operates between T1 and T2. Any other type of cycle will result in a lesser value of efficiency. Okay, so just make a note of this, people. Okay, now next thing we will look at the schematic of the reverse heat engine. Yeah. Or a refrigeration cycle. So the schematic of this looks like just a reverse of what we had seen for heat engines. So in this, what happens is that work is done on the cycle. So work done by the gas, okay, is equal to minus W per cycle. Okay. W is equal to the work done on the gas per cycle. Okay. And in the process, Q1 amount of heat is extracted by it into the heat sink, whereas Q2 amount of heat is provided to it by the heat source. Okay. So the net heat is equal to minus Q1 plus Q2, or minus of Q1 minus Q2. Okay. Q1 is greater than Q2. So this is the net heat supplied to the gas, and that is a negative quantity. That means heat is extracted from the gas as work is done on it. The work is done on the gas and heat is extracted from it. So that is the job of a refrigerator. Okay. So here the efficiency, it is defined as the heat extracted per unit work done. Okay. Now from these two you can see that W net is equal to Q net. So minus W is equal to minus Q1 plus Q2. So again, W is equal to Q1 minus Q2. Okay. So here, this becomes this much. So this is the definition of efficiency. It is heat extracted from the gas by the heat sink per unit work done on the gas, okay, during one cycle. So the efficiency has the inverse formula of efficiency that we had for heat engine, because the process is running in reverse in comparison to the heat engine. So just make a note of this, people will wind up with this. Okay, so with this formula, we complete the portion of heat and thermodynamics. Okay. So please complete the required exercises from HC Verma in your module. Okay. And next up, we will start the discussion about heat transfer. Yes, heat engine and all this is part of NEET also, Jesh. Okay. This portion of first law of thermodynamics and its applications, including heat engines and refrigeration cycles and everything, it's part of the NEET as well as the JEE syllabus. Yes, next chapter, next lecture, we'll be starting the new chapter of heat transfer, that is conduction and radiation. Those are the things that we'll be studying in that. Okay. So that's it for today's session, people, and wish you all the best.